Welcome to the last lab of Chemistry 111, the VSEPR theory lab. This is not so much a lab as a worksheet. So I'm going to go through basically how you should approach this one. You technically could be using models, but you do not have to have any models. And so what we're going to be doing is going through systematically, looking at the Lewis structures, drawing them out, and finally going through the following steps for these guys. So I'm going to start by sharing screen and we'll look at the lab together. So look at the Lewis structure lab. So each problem, there's a ton of problems, all the same general premise. You give a Lewis, you'll give a formula. You must first draw a Lewis structure, and a valid Lewis structure where all charges, all electrons are accounted for. And then we'll go through the following steps of what is the electron domains, what are the bonding domains, what are the lone pairs, what are the ideal bond angle, what is the actual bond angle, what is the electronic geometry, what is the molecular geometry. Where you draw this in 3 dimensions, showing the lone pairs and a dipole moment if there is one. Determine does it have a molecular dipole, and finally determine the hybridization. It seems like a lot, but there's a bunch of charts earlier on that can help you. So jumping back, you'll see here the following half a dozen charts. They're explaining hybridization. So this chart right here, table 2, is used to determine the hybridization. You need to look at the number of electron domains, and that will directly determine the number of hybrid orbitals and what type of hybrid orbitals you have. So you literally, if you correctly determine the number of electron domains, you have that. There's on bond polarity right here, talking about whether we have polar or non-polar, how equal and opposite cancel out. You also look at electronegativity. Electronegativity, you have to compare electronegativity between 2 atoms to see whether it is a polar bond. And bond geometry. So right here, steric number, this is the number of electron domains. The total number regardless of how many lone pairs. So you'll look and determine the number of electron domains in your Lewis structure. And then you'll look how many lone pairs are in your Lewis structure. Looking at that, that will give you the geometry. Now this base geometry is always going to be the ideal geometry. Regardless of how many lone pairs you have, this is going to be your electronic geometry, and you're going to be ideal bond distance. Now, your molecular geometry is going to be whichever blank it is when we talk about the lone pairs. So you could have both your electronic geometry and your molecular geometry being the same if it's a tetrahedral structure with 4 bonds, no lone pairs. But you could have a tetrahedral electronic and a trigonal pyramidal molecular geometry if you have 1 lone pair. So you'll get your ideal bond angle and your actual bond angle from here, as well as your electronic geometry and your molecular geometry from there. I'll show you wedges and dashes to say going forward, coming towards you, and going away from you. So, okay, going back to the first structure. So you notice here, PCl5. You look at phosphorus. Where is phosphorus in the periodic table? It is in group 5. It has 5 valence electrons, so it can make 5 bonds. You draw 5 bonds from the center atom to all the chlorines, and you have this structure. The reason I made these structures is for you to see this. You can spin this around. This is this gray ball has 5 holes. I have put 5 atoms on it. Now you can see that. Now, how many electron domains does it have? Well, there's 5 bonds, 0 lone pairs. Total number of electron domains is 5 plus 0, or 5. It breaks it down. Electron domains is just things coming off of the atom. Bonding domains are how many of those things are bonds. Lone pairs is how many things are lone pairs. The sum of the bonding domains and lone pairs will always add up to the number of electron domains. So blank 2 right here should always equal blank 3 plus 4. Looking back on that table, so 5 electron domains, 5 0 lone pairs means it's right here, both in electronic and molecular. So the bond angles in ideal and actual are the same. You get these right from that table. But if you look, this is a trigonal bipyramidal structure. You have that triangle right here, 3-atom triangle, and draw this up. We have a pyramid up and a pyramid down. Trigonal bipyramidal. Now looking down, drawing this 3 dimensions. You see right here the wedge and dash. I'm holding it right like this. This atom is going towards the camera. This atom is going towards me. Wedge and dash to say these guys are flat, equally distant from me and the camera. Now looking at that structure, even though phosphorus has a dipole electronegativity of 2.1 and chlorine has electronegativity of 3, this would be a polar bond. But equal and opposite cancel out. Up cancels down. These left cancel right. This front cancels back. So we have polar bonds, but non-polar molecules. So this is not polar. It's no molecular dipole. Hybridization. 5 things coming off. If you look at the hybridization table, it says sp3d for this guy. So there is our structure. Now sulfur. Sulfur is group 6. It should have 6 electrons. Oxygen is group 6, also have 6 electrons. As you draw this guy, you will say, oh, oxygen needs a second bond to make to give it an octet. Sulfur, being row 3, is allowed to make more than 2 bonds. It is allowed to have more than 8 electrons. So sulfur has 5 things coming off it. So I'm going to use that same gray molecule. See these springs? These are our double bonds. So looking at this, you can't necessarily tell by this shape, this picture, right, this Lewis structure, but the shape, you might be able to say, oh, this is not linear, this is actually bent. And with this lone pair without an atom up here, you can say, oh, this kind of looks like a triangle, a flat triangle. So looking at this thing, double bonds still count as one bonding domain. So we count 1, 2, 2 bonding domains. We have 1 lone pair, They add up to 3. Going back up to our structure, 3 electron domains is at 120 bond angle. It's trigonal planar. But 1 lone pair puts us at bent or angular or less than 120. So you'll start filling that out. Now looking at this, we look at the electronegativity of sulfur versus oxygen. Sulfur is 2.5, oxygen is 3.5. This is clearly going to be polar. Now, if this was linear, the oxygens would cancel out, but being bent, means this oxygen is pulling down into the right. This oxygen is pulling down into the left. The dipole is right between the middle, straight down. So is this polar? Yes. How many electron domains? 3. So that is sp2 hybridized. So looking at that. So let's just quick look at some of these structures real quick, just to help you picture this. So this guy is your trigonal bipyramidal. If I remove one atom, still have that lone pair blank there. Now it's our seesaw. Seesaw, it's seesaw and backboard. If I remove another atom, it's going to become T-shaped. If I remove another atom, it finally becomes linear. But that requires us to have 3 lone pairs. Or you could also imagine that guy from your trigonal planar perspective. You could make that same structure with this guy. Just put them on the edges, no on the side. Now our octahedral. Our octahedral structure is essentially an 8. If you drew lines between all the atoms, you would have an 8-sided dice. You'd have a square pyramid on top, a square pyramid on bottom. Octahedral, the 6th atom. Now, if I start removing one atom, doesn't matter where, I now have what's called the square pyramidal. So I remove the bottom pyramid, it's just a top pyramid. If I remove another atom, I'm going to remove it from the opposite side. So now it's square planar, flat square. If I remove another atom, we would have T shape, and another atom would have linear. But don't think we're going to have that. Final major structure is tetrahedral. Tetrahedral is a 4-sided dice. It's a triangular pyramid, but it's equilateral. All sides are the same shape. So I could rotate this and it's the same. Same. When I pull one atom off and replace it with a lone pair, it becomes trigonal pyramidal. It's a squat pyramid, essentially. If I remove another atom, it becomes bent. This is our basic water molecule. So one of the rules you need to know as you're working through this, as you're looking at your molecular dipoles, any atom that has all of the same atoms on every side and is adopted the same molecular geometry as electronic geometry is always nonpolar. So PCl5, all the same atoms, these two geometries are the same. But if the atoms are different or they're not equal and opposite, then you can have polarity. So you'll be doing this. Note the center atom is going to be nitrogen. Center atom is going to be carbon. The center atom is going to be carbon. Now this guy, even though this guy is going to be, I'll give you a hint, tetrahedral, there's a hydrogen which is different from the 3 chlorines. And so this guy is definitely going to be polar. Center atom arsenic, oxygen. One of those 3 oxygens is going to be the center atom. But it's not going to be a ring. It's going to be a antimony, center atom, chlorine, the center atom, sulfur, one of those iodines will be the center atom. Please note, some of these guys have charges, so you'll add an extra electron when counting those. Phosphorus, bromine, radon, xenon, all center atoms. So you'll work through all these. Beryllium, the center atom, carbon, the center atom, nitrogen, and nitrogen. So some of these guys, these pairs will follow trends. there may be on one page, all of the electron domains add up to 5 or add up to 6. So there'll be a trend on each page. So one may not all the way through the page, but there will definitely be pairs of trends. One page may have all 4 structures. You got to work through them. Take your time. It's not hard, but you do have to make sure that all of the atoms surrounding the center atom have achieved either octet or hydrogen's doublet. All of the atoms around the center should have an octet or a doublet. If you do not have that, you do not have a correct structure. So take a look at that, work them through. It's not overly hard, but it's a lot, so don't wait too long. Okay, I just wanted to give you a quick run through. You have to work through that, but it's not a bad lab. So have a good day, good luck, keep working. See you maybe next year. So this has been the Chemistry Cowboy. Once again, if you like what you see, please like, please subscribe. I'll be posting more videos to give you the education you need. And I've been asked to put this disclaimer to Bethel students. Remember that the log and the online learning guidelines remain in effect while interacting with any type of instructional materials / sessions. That over and out.